Okay, thank you for coming. Appreciate you being here. Happy Tuesday. So just to remind you, homework one, which is where you draw something to the graph, is due this Thursday. So the next class period. If you drew it on paper and you want to turn in a hard copy, bring it to class, or anytime before, like if you don't finish it by class time, then there's in my office in Galileo 103A, there's a box right outside my door, and you can just slip it in the box. And then I'll pick it up when I get back into the office. Also, if you did it on the computer, or maybe you want to scan it and turn it into Canvas, that's also an option. I've decided that the homework 2/math packet is going to be due a week later. So homework 1 is due this Thursday. Homework 2 is due the following Thursday. All right, so my plan is for us to just start chapter 2. So we've gone over kind of what's a graph in general, what can we use it for? And now we're going to start like actually talking about definitions and drawing some pictures. And so the way we're going to do this, so if you have the textbook, I think this is one way that you can follow along, especially so the chapter 2 in the textbook, I'm going to go pretty much through. I might skip a few things, but a lot of the definitions and diagrams are really helpful to kind of learn what's going on. So this is a place where I think the textbook is useful. In the chapters following, I may not go through everything. I may skip around a bit, but since this is one of the foundational chapters, we kind of have to take our time and get acclimated to this. You'll also notice that this chapter ends up being like, how many pages? So from like 26 to 57 or so. So it's like 30 pages. That's because it's really important. Okay, here I have something for you. All right. The way we're gonna do this is kind of old school math where except I'm not gonna write on the board because I like to preserve the things that I write. So I've got my drawing tablet thing, and let me open up. Okay. I've got this Word document where I am going to, if we make it a little bit bigger, um, I'm gonna like draw on it and write it out. And so hopefully that is better than typing because I type faster than I handwrite, and you would probably either be typing or handwriting. So kind of slows it down, gives our brain a chance to catch up. And also it lets me draw like pictures that are hard if I'm just typing things. Okay. This is also the first time I've done this as an instructor. So we'll try it out, see how it goes, and can adjust if needed. As we go, if you have any feedback or things that I could do to improve, then let me know. I'm happy to make adjustments. Okay, so we're going to start just at the beginning of chapter 2, where we are talking about graphs, as you may have guessed. So they've got a definition where this is my abbreviation for definition, where we say that a graph G consists of a set of vertices and a set of edges. And we say that each edge each edge joins two vertices, right? This is the definition that we saw in chapter 1. So I added this G here just because it's typical to refer to a graph as just the capital G. We can refer to the set of vertices as a capital V and the set of edges as a capital E. And so with this, we can write G equals V comma E. And we typically write it with parentheses around them to show that G is some pair where V is a set and E is a set. This is why we need to talk about sets. Okay, so let's look at the graph that they've got in the book, where it starts off with something like this, where we've got 4 vertices, where we can write V as a set. Remember, we write sets with curly brackets. And so we can label them. So like this is U, this is V, the bottom left is X, bottom right is W. And so we can write the vertices as a set. The vertices is just a regular set. So we can say U, V, W, and then X. That's my set of vertices. And then from here, I can draw edges. So we've got a triangle here with U, X, and W. X has this edge going to itself. W and V have, one edge. No. Come back. Okay, where'd we go? Got this. We've got this. Got one here, one here. Great. So when we go to write the edge set, we can do it a few different ways. One way is we could number the edges, where we could say this is 1, this is edge 2, edge 3 and 4, 5, and 6. And so in that way, we could write the set of edges as 1, 2, 3, 4, 5, and 6, right? That's one possible way. Another possible way, which you'll see, we can write them as pairs. So if we didn't want to number all of them, we could write them as like U and X, that's one pair. U and W, that's another pair, and so on. Sometimes it gets kind of tedious to write like parentheses, comma. And so another way of doing this is to just say UX is one pair and just write the name of the vertices, smush them next to each other. So we could write UX, UW, WV. We could write either WV again or VW. The thing about this is unless the graph is directed where there's arrows on the edges, the order when you write the edges down doesn't matter. So I could have written it as XU instead of UX, and that's fine. Same thing. Okay, so we've got 3 and 4 here, and then we need XW, that's 5, and then XX is 6. Okay. Yeah, so you may have noticed that this graph has some redundant edges, you might think. So we saw the example with like the football teams where in a series of like we take a subset of games from the season And in that subset, some teams play each other more than once. And so in that case, this double edge between V and W might make sense. But typically we tend to disregard this. So some definitions for you. I need to do that. Let's move this over here. Okay, so another definition for you. What we call here is a multiple edge between W and V, because there's one edge from W and V, there's another one. And so we call a multiple edge as when we have at least two edges joining the same pair of vertices. And so the example here is VW or WV, which happens twice. What we call a loop is an edge joining a vertex to itself, right? So that's the example of XX in the graph above, right? Where we've got a vertex X and there's just an edge that loops back to itself. That's a loop. So then what we call a simple graph is basically just a graph with no multiple edges and no loops. Okay, how do we add another page? Sorry, link page. There we go. Are we good to go? Anyone need more time? All right. So a simple graph is just no multiple edges, no loops. So for example, the way to draw the previous one as a simple graph is to just take away the multiple edges, take away the loop. That's a simple graph. Yeah, okay, so this is so I've got the packet. The packet for this chapter is just the in-text problems because I like them a lot and I think they're useful for understanding. So I've taken pictures of each of them and then put them in a Word document. So this is you want to spend the few minutes, maybe talk with your neighbor, do the first two of the packet problems. And I'll give you till 10:28. Okay. So for the first one, is the one on the left simple? No, right, because we've got that loop right here. What about the one on the right? Is it simple? Yeah, no loops, no multiple edges. Can I get a volunteer to draw, or two volunteers to draw one of their either A or B up on the board over here? Cool. You want to do A or B? A? Can I get someone to do B? Right. There. Yeah. Yeah. Sure. I figure that's the whiteboard that no one's sitting at and is not covered by the screen. Can you draw it though? Oh. So like for A for problem 2, like if I draw the dots for the vertices, and then when you have the edges, connect the vertices together. Okay, so over here for B. Also, wait, I'm not sure that there should be only 4 edges for problem 2. A. The one in the middle. So you're looking at the first line there. So where the vertices are
Wait, are we doing 2.1?
2.2.
Oh, I thought we were doing 2.
Oh, no, sorry. Yeah, please, 2.2. Okay, so for B, we've got 1, 2, 3 boards across, and then 5, 6, 7, 8. Okay, so then 1 goes to 2, there's a loop on 2, 3 goes to 4, also 2 goes to 3. We've got this one, this one, this one. 3 goes to 4, 3 also goes to 5. 6 goes to 7. 6 goes to 8. And 7 goes to 8. Is it simple? No. And so for A, thank you. That's great. We've got U, V, W, and X. U goes to V, V goes to X, W goes to X, and V and W. And it is simple. Awesome. Make sense so far? Cool. All right, so now we need a new definition. So we're going to say that vertices, let's call two vertices V and W. We tend to just come up with letters like in algebra. So remember, this means, wow, I'm so bad at drawing curly brackets. Remember when we talked about this symbol for sets, which says that something is in a set? Vertices is a set, and so this means that VW are in the set of vertices. So that's how we read that little bit of notation. So these vertices are adjacent. We say that their two vertices are adjacent if they're joined by an edge, which we can denote E in capital E. So lowercase e in capital E. This is fairly common where if we just want to refer to an edge, we'll use a lowercase e. And since E stands for edges, that clues us in that we're talking about an edge. Okay, so two vertices, we call them adjacent. So we can draw that as we've got V on one end and W on the other end, and a line E in the middle. V and W are adjacent. Okay. Then to kind of flip it around so we can talk about E for a second. So we say V and W are incident with E. So V and W are adjacent, and then to talk about it in terms of E, they're incident with E. And so we can also say that E is incident with V and W. So in the one for A, the U and V are adjacent, right? And the edge, if we named it 1 between U and V, edge 1 is incident with U, edge 1 is also incident with V. Okay, so then there's another packet problem. Number 3, which we can probably just talk about. So we've got the graph on the right here. And are V and W adjacent? Yes, because there's two options here. There's 4 or 5. Are V and X adjacent? Here's V, here's X. No, because there's no edge between them. Is vertex U is incident with edge 2. Here's vertex U, here's edge 2. Are they incident? Yeah, because U's edge 2 is connected to U, vertex U. And then edge 5 is incident. Edge 5 over here is incident with vertex X. Is that the case? No, because they're not connected to each other. They're two different parts of the graph. Okay, so A, yes, B, no, C, yes, D, no. All right, so a note about the way that we draw something. So when we draw a graph, that's generally good enough. So the orientation of how we draw it in space doesn't really matter. So we've got the one over here where we've got the 4 vertices where we drew it like this. If we drew it like, maybe if we like flipped it over and maybe stretched some things out. So if this is UV, XW, let's say if we rotated it this way, so then this is U, this is V. This is X, this is W, did I get that right? So where we've like flipped it over and stretched it out, it's the same graph. So the orientation in space doesn't matter. We can move things around as we like. So an example they have in the book is, if you remember the utilities graph, where we can draw it like this, where we've got house A, B, and C over here. And then we've got our 3 utilities where we have G for gas, W for water, E for electricity. And then we can connect A to gas, water, and electricity. We can connect B to gas, water, and electricity, and house C to gas, water, and electricity, right? We can draw the graph like this. We could also move it around. So another way to draw it is, I'll draw out all these dots and then I'll label them. So we've got house A over here, B over here, C over here, and then we've got gas, water, and electricity. And so A gets connected to water, electric, and gas, and so on for B and C, right? The graph looks like really different to me, but it's the same graph. We've just moved things around. Something that's not the same. We want blank page here. Okay, this is something that I have to work on. No. Okay, now I have like 5 blank pages. Can I move them around? There we go. Okay, so if we've got the graphs, close this. Apparently not. Okay, whatever. So let's say we label either of these as G1. Let's make a graph called G2. And it's gonna look the same, where we've got 3 independent on the top, 3 independent on the bottom. And we draw those edges similarly. Right? So each of the 3 is connected to each of the other 3. But we label it differently. So let's say that this is G, and then maybe B and E. And on the bottom, we've got A and C like before. We swapped the labels. This is not the same graph because in the previous ones, A, B, and C are completely independent. So even in the redrawing, A and B, there's no edge between them. A and C, no edge. B and C, no edge. But over here, we've got an edge between A and B and C. So that makes this not the same graph. So we can say that G1 is not equal to G2 purely because of how we've labeled it. And so we say G1 is not equal to G2 because AB is in the edge set of E2 and also BC. But AB and BC were not in the edge set of graph 1. You'll see the use of subscripts in here, which is like a little number below the letter. So we read this as G1 and G2, graph 1, graph 2. And then the numbers also extend to like the vertex set and the edge set. So like E2 can be read as the edge set of graph 2. E1 is the edge set of graph 1. Okay. So from this, we get a new definition. So we can say that two graphs, let's call one of them G, the other one H. These two graphs are what we call isomorphic. And that's what means that if we can get H by relabeling the vertices of G. And so we can do this, like if we relabel G2, we can get G1. So that's just swapping B and W. So like we can look at it and it has the same structure, but if we just swap the labels, relabel, we can get G1. The kind of math definition that the textbook has is that something is isomorphic if there exists, which if you've taken discrete math, you might recognize that symbol. The backwards E just means there exists a one-to-one correspondence between the vertices of G and the vertices of H, such that, so there's going to be a correspondence where we can draw something from the vertices in one to the vertices in the other, such that the number of edges in G, that's a weird looking G, has to equal the number of edges in H. And the corresponding pairs have to be equal. And so once we find that correspondence, we say this one-to-one correspondence is an I'm not gonna have enough room. Isomorphism. Okay, so the example for this is we're just looking for, can we relabel them? And can we relabel every vertex in one and every vertex in the other to have them be the same? So for an example, we've got a 4-vertex graph. One's U, one's V, one's X, and W. W's got a self loop. Two edges between U and V. X, W, and then one from U to W. Okay, so that's one version of the graph. This is G. No, that's not 2. That's 3. No, that's not 3. That's 2. 1, 2, 3, and 4. We've labeled it. I think I missed an edge in here. Somebody have the textbook open. You know what edge I missed? Or maybe. Let's find the isomorphism and then we'll figure it out. Okay, so if this is H. Okay, so we can, it's kind of easy to see where if we look at the loop, W and 2 should be the same vertex. So we can write W and 2. U and V, since they've got that loop, I think that's the one that I missed. U and V, the one with the multiple edges. So we've got 2 options, 3 and 4 for U. Which one should U go with? 4? Yeah, because U's got the edge going to the one with the loop. So U should go with 4, and then V should go with 3. And then X, as the corner here, should go with 1. And so if we relabel these and then we look at the edges and we see that the number of edges is the same. So if I had actually forgotten this, then we would say that these 2 graphs are not isomorphic. But since we can say this vertex should be swapped with this vertex, then we can say that these 2 graphs are isomorphic. Okay. Okay. Consider these 2 graphs. Do they have the same number of vertices? Yeah, right, there's 5. Do they have the same number of edges? Yeah, there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So another way to write the number of things in a set is to use the vertical bars around the set name. So V is our set name, and so I've written these two vertical bars. If you're typing this on a keyboard, this is probably the pipe character, which can be found on my computer. If you press Shift, it's the one above the Enter key. So let's see, let's call this one G, this one H. Number of vertices in G is equal to the number of vertices in H. Number of edges in G is equal to the number of edges in H. Are they isomorphic? Can you, like if we choose to label them, can we find this correspondence? I see head shaking. Why is that? Go for it.
First graph, this is where to see with 4 edges. And second, there's
Yeah. So we'll talk about degree in a bit, but the degree of a vertex is how many edges does it have? So like this one has degree 3, this one's got 2 edges, so it's degree 2. And this one over here has 1, 2, 3, 4 edges. But the equivalent one in the other graph only has 3. And so just by looking at the way that we've drawn the edges, we can see that these two graphs are not isomorphic. So G and H are not isomorphic. Okay, so now, whoops. If you want to look at 4 and 5, and I'll give you, let's see, maybe until top of the hour. Probably won't need that long. All right, does anybody need more time? Okay, let's go over. So we'll probably, yeah, let's go over 4 and 5. So what's the isomorphism relabeling for 5A? Can I get a volunteer? Sure.
So 1 is B, 3 is B, 4 is A, and 5 is C.
Wait. Sorry, I think I misheard. Is 5 is B and 2 is
D.
D. Got it. Okay. Right, so yeah, so this is 1. This is E with the self loop is 3. That's 5. And wait, no. A is 4. And then D is 2. Yeah, question.
Yeah, so you know how A and D both just have like the two edges?
A and D both have 2 edges. Yeah.
Like, could they be like swapped then?
Could they be swapped?
Like, instead of 4, or A being 4, A being 2, like it doesn't matter which one.
What do you think? See head shaking. Why? Or does anybody else have an idea? Go for it.
They're adjacent connected to different verse. So 4 is connected with, or A is connected with 5 and 3. And then D and 2 is connected to 1.
Right. So and I think the important thing here is like looking at what is adjacent here, where C's got this self loop. D is connected to E with the self loop. Wait, no, sorry. A is connected to E with a loop, and B. D is connected to E with a loop and C. Right, and so because these two, like, because this edge is different, then that's why we can't interchange them. Does that answer the question?
Yeah.
Cool. Any other questions? Awesome. Someone else have an answer for B? Yeah.
I had but T was minus. T is equal,
T is equal.
and then P is times.
P is times.
R is division.
R is division. That's division. Yeah. Anybody else get something different? Cool. Yeah, so they're equivalent. All right, how about for problem 5? Are they isomorphic? No. Why not? Yeah.
The two vertices, 5 and 6, are adjacent to
corner vertices, but they're also adjacent to each other, then no such pairing exists in the other graph.
Yeah, because if we try that for like E and F, they're adjacent to each other, but F's not adjacent to a corner vertex. And if we look at the two vertices who are adjacent to a corner vertex, E and G, they're not adjacent to each other. Yeah, that's a really good explanation. Thank you. Any questions on that? Okay. Okay, so far we've been looking at what we call labeled graphs, where we've got vertices and we've named them. We can also ditch the labels if we want to. So that's, for example, something like if we have let's try that again. So let's say we've got W, what's this in my notes? V? No. U, V, W, and X. So if we've got a graph like this, we can ditch the labels and move it around however we want to get what we call an unlabeled graph. So let's move, I think it's U to the middle, or maybe it's W to the middle. So we've got something like this. This is also adjacent here. And I've missed an edge. Okay, so we ended up moving W to the middle. Right, so we've ditched the labels, moved things around. They're still isomorphic. So another definition for isomorphic, especially when we're dealing with unlabeled graphs, is where we can assign labels such that the graphs are the same. So if we have these two graphs, we can just take the labels from U or from the one on the left and then assign them to the one on the right, and then they're isomorphism. In general, so you'll see going forward either labeled or unlabeled graphs, sometimes with the varying number of L's, depending on how British we're feeling at the moment. And so it should be clear, like if there's labels with a vertex, then it's a labeled graph. If there's no labels, then it's unlabeled. Okay, so then I think we've got packet problem 6. So I'll give you like 2 minutes to do this. So then we'll go over this problem, and then I want to talk about the last one in the math packet to close us out for today. Okay, so from 6, what's our labeling? Maybe let's label one of them first and then see how it shows up to the other one. So zoom in a bit. It kind of depends on personal preference. I remember being in a class, I took some graph classes in grad school, and the way that I would label a graph would often be completely different from the way that the instructor was doing it. So if I go to label things, then it may be different from how you do it. But that's the thing about isomorphism. It's the same thing. Okay, so let's say A, B, C, D, E, F. So I think what happens is B, C, and E, the inner ones, get expanded out, right? So first let's look for a triangle, A, D, and F, right? That's the original big triangle. And then let's see, A is adjacent to B and C. C is adjacent to F. C is also adjacent to E. E is adjacent to B and C. That's that little triangle. And then E, D, and F. Think I got everything? Yeah. So if you've labeled it differently, that's fine. Okay. All right, so next time we'll pick up with subgraphs and counting things. I want to take a few minutes to talk about the last problem on the math packet. I'm worried that, is this the one that I drew on? I don't think so. Oh, it is the one that I drew on. Okay. Let me delete these. I drew on it in the other class. Because I want to make sure that we have the correct equation. Okay, good enough. Okay, so the question for the last one is, what's the minimum number of breaks to break up this chocolate bar? And then we want to prove the number by induction, right? That's what the question's asking. So the first thing to approach is to find out, what about for this bar? How many breaks for this bar, which is 4 by 1, 2, 3, 4, 5, 6, 7. Did anybody get an answer for how many breaks for this chocolate bar? Someone who's not in 374. Okay, so the process that I would take to figure this out is, let's assume I've got this chocolate bar in front of me. We've got two choices here, right? First is I can break it into rows, right? I can break it into rows and so on, or I could break it into columns. So first I could go from the top down and break the rows, or I could go left to right or right to left and get columns, right? Those are my options. So let's say I do rows first. So to get 4 rows, I have to do how many breaks? 3. 4 rows. So we look at the edges between them. Where'd my mouse go? 1, 2, 3. And now if I've got my rows, how many breaks? Let's take just 1 row. So I've got 4 individual pieces of chocolate now. How many breaks does it take to break just 1 row into the individual pieces? So I've got this top row. How many breaks does it take? 6? 1, 2, 3, 4, 5, 6. Yeah. Okay, so now, and so now I've got my 7 individual pieces of chocolate. To get the rest of the pieces of chocolate, I have to do 6 breaks on this row, right? 6 breaks on the next row, 6 breaks on the following row. So I've done 3 breaks initially to get them to the rows. And then I did 6 breaks to get 1 row. And then multiply that by 4 to get all the rows. And so that gives me, man, when I stand up here, I cannot do mental math with a lot of confidence. 6 times 4 is 24, plus 3 is 27. So that's the number for this chocolate bar. The goal is to do it for a general chocolate bar. So at this point, now that we know it works for this specific example, now we want to come up with a general formula. And so the general formula, we've got 3 plus 6 times 4. So we want to abstract this chocolate bar a bit. So we've got our height or our length and width. Like we've got the long side, we've got the short side. So now the step is to assign 2 variables. We'll call them n and we'll call them m, and just assign one of them to one side and the other to the other. So I don't remember what I did in mine. No, I think I did n here and m here. This is the part where I have, without loss of generality, this is the part where we could have chosen to swap them. We could have had the 4 be m and the 7 be n, right? Could have done it either way. So we've done that, and now we have to write our process of what we just did in terms of n and m. So if n is 4 and m is 7, what's 3 in terms of n? N minus 1. And then what's 6 in terms of m? M minus 1. And then what's 4? N. Right. And so, and again, we can read this formula to say that the n minus 1, that's where we broke the rows. And then we've got n rows after that. And to break each of those rows into individual pieces, we have to break that row m minus 1 times. This formula, if we chose to break it into columns, it's going to be the same thing, just I believe with n and m swapped. So if you get something, if you have n and m that are swapped, then that's okay. It's the same kind of style. So then to prove this by induction, we can say that so for induction, we're trying to prove a premise, which is typically in terms, let me try and open it. 485. So we proved that the sum of things up to n is n times n plus 1 over 2. We could say this is our premise, P of n. But the thing is with this, we're working in terms of two variables. So whereas with normal induction, we did P of n, and then we assume it works for P of k, and then we prove P of k plus 1. Here, we're going to assume that it works for, we've got P of n and m. Assume that it works for maybe I and j, or j and k. The letters don't really matter. And then you have to prove it 3 different cases. So the idea with induction is we increase 1, but we've got 2 variables, so that gives us 3 different options. One is I plus 1 and j stays the same. One is where I stays the same, and we do j plus 1. And the other is where we increment both of them. Okay, so take a stab at that, finish up homework 1, and then work on the packet, homework 2. And I will see you on Thursday with your completed homework 1. Thanks. See you next time.